So this is a reading that I gave to you through a link in an email. And let's just get right to it. This reading really addresses the question, how does matter behave in the presence of thermal energy? And you know what? This question could just as easily be stated, how does matter behave in the absence of thermal energy? In other words, how does matter behave in cold? Because matter basically does one of three things. Matter gains energy or heat. It holds energy or stores it. And matter can release energy as it cools. So let's read this and we'll get some of these things underlined. When molecules of any kind of atoms get more energy in them than they had before, they move faster, and we call that heat. So what is heat? Heat is when molecules move faster and faster. So when molecules move faster, they hit against each other and bounce apart. So they end up further apart from each other than they were before. So what's going on here is when molecules move faster, they actually spread apart. And they spread further apart than they were before. Now, energy can come from sunshine, volcanoes, from friction, nuclear fission, many other sources. Heat energy can come from lots of different sources. But I want you to think a moment about taking a stone or a big rock, rolling this rock into this fire. And you leave it in the fire for 1 hour. After 1 hour, go ahead and roll the rock out of the fire. And let's think about what happens to this rock. So first of all, when it was in the fire, the molecules were moving faster, further apart. It was gaining heat. You left that rock in the fire for an hour and then you rolled it out. The air around the rock now is cooler than the rock itself, so the rock is going to begin to release energy. That rock is beginning to cool as it sits next to the fire now. Also, when that rock was in the fire, it actually expanded. The rock physically got bigger. It got bigger. You couldn't see it. If we were to have taken calipers and measured it, it's measurable. Some matter will expand more than others. For example, brass will expand a lot more than, say, steel or rock would expand. But that rock physically expanded. It got bigger. And when we rolled it out of the fire and out to the side, let it start to cool, the thermal radiation that the rock had stored in it began to cool. By the way, you can just show that it has thermal energy in it. Okay. But that rock started to cool, and as that rock cooled, it actually got smaller. The molecules slowed down until it got back to the air temperature around it, which might have taken an hour or two, or it depends on how cold it actually was. Let's just get these last two statements here. Things are hot if their molecules are moving quickly. So heat is directly related to the molecules moving faster. That's what's actually happening. When molecules are moving faster, the substance is gaining heat and has heat. And they're colder if their molecules are moving more slowly. And this is kind of interesting, and we'll do a double underline here. Temperature is a way of measuring how fast the molecules are moving. So if something's got a higher temperature, the molecules are moving faster. If a substance has a lower temperature, its molecules would be moving more slowly. So let's look at the last 3 paragraphs of this reading. If two things are touching each other, heat will flow from the hotter one to the colder one, unless they are the same temperature. If you want to think about the objects in a classroom, and if we put all the objects in a freezer, and then we put the objects out into the classroom and leave them in the classroom overnight, by morning, all of those objects will be the same temperature as the air in the room. So if two things are touching each other, heat will flow from the hotter one to the colder one, unless they are the same temperature. So this is true also of air. The molecules of the hotter one will slow down, and the molecules of the colder one will speed up until they are all moving at the same speed, and the two things have the same temperature. For instance, if you put an ice cube in your mouth will get colder and the ice cube will melt until the ice cube and the mouth become the same temperature. And by the way, we call this two things touching, the heat will flow from the hotter one to the colder one. We call this conduction. That's where one object conducts heat to another object. When molecules are cold, they are not moving very much. They are usually very close together, like a crowd of people standing still. But as they heat up and move faster, the molecules begin to bump into each other and bounce off, and they bump into other molecules, and soon they are farther apart from each other. Because of this, hot things have more space between the molecules than cold things. Get your blue colored pencil. Because of this, hot things have more space between the molecules than cold things. And the same number of molecules takes up more space when they are hot. The same number of molecules takes up more space when they are hot. If you boil water in a pot, it will turn to steam. And those water particles that are turning to steam will go out into the room because they need more space. Because hot and cold are ways of talking about how fast molecules are moving, and there are so few molecules in space, we're talking outer space here. Space really doesn't have any temperature at all. We think of space as being cold, because if you put something made of molecules in space, like yourself for instance, you would get cold as your heat moved away from you, evening out the energy difference between yourself and the space around you. In fact, you'd wind up just going down to like what we call absolute zero. Which is actually 0 degrees K, because there's a whole nother scale of temperature that you may or may not know about yet, but it's called the Kelvin Scale. And under the Kelvin Scale, 0 degrees K is actually equal to negative 237 degrees Celsius. And what we say is matter ceases to move at that temperature. In other words, the atoms at negative 230 degrees Celsius, which is 0 degrees Kelvin, which is what we consider to be absolute zero, atoms don't even vibrate anymore. Atoms and molecules won't even move. They become absolutely still and cease to move at that temperature. So this reading is kind of interesting. The main things you need to take away from this: how does matter behave in the presence of energy? Well, the molecules and the atoms that make up matter, they start moving faster in the presence of energy, in the presence of thermal energy. And the more thermal energy that they absorb or that they gain, the faster the molecules move. As matter cools or releases thermal energy, the molecules and the atoms begin to move more slowly. They slow down, they come closer together, and they pack in tighter and tighter until, if you were to take matter all the way down, if you could take matter all the way down to negative 230 degrees Celsius, those atoms and molecules would cease to move altogether. They just would not move anymore at all. And we would say that they have no more energy to release. So think about this. Does an ice cube, which freezes at 32 degrees, does an ice cube have any energy that it can release?